All right, let's dive right into this explainer on how the Adelic Langlands program actually constructs a universal, completely equation-driven proof for Green's conjecture. If you follow algebraic geometry, you know this is a literal mountain we've been trying to scale for decades. Today, we're letting the math do the heavy lifting to finally reach the summit for all curves. We've got a ton of fascinating math to cover. We are going to walk through the arbitrary curve problem, build the Koszul to Hecke dictionary, look at resolution flattening via Satake, dive into L functions and prim fibers, stabilize some ramification defects, and wrap it all up with the grand synthesis cycle.
So part 1, the arbitrary curve problem.
Historically, proving Green's conjecture for arbitrary curves just hits a brick wall. Why? Because exceptional linear series totally distort the canonical ideal's resolution path. To dodge these localized algebraic knots, we actually have to lift the arbitrary curve to the moduli space of Higgs bundles and then hit it with the adelic lift to the adele ring. This sequence is absolutely crucial. It takes Koszul cohomology, which is a notoriously brutal nonlinear problem, and transforms it into a highly solvable spectral stability problem for automorphic representations.
This setup brilliantly illustrates the contrast. Think of the messy, nonlinear geometry of geometric distortions, where special syzygies create these frustrating localized knots. Well, we are abandoning that completely. Instead, we're dropping down into a clean, universal error-correcting template of linearized Hecke modules. We are basically redefining syzygies, not as elements of Tor groups, but as ground-state obstructions or null modes of a generalized Dirac operator over the adele ring.
Moving right along to part 2. The Koszul to Hecke dictionary.
In this translation table, classical Koszul groups map directly to the Ext groups of Hecke eigensheaves. So you have classical scheme geometry on one side and the geometric Langlands counterpart on the other. We're literally framing syzygies as multi-particle ground state obstructions. A curve C becomes the moduli stack of bundles, and the minimal free resolution translates perfectly into a derived category decomposition. It is a stunning one-to-one mapping of geometric frustration straight into field theoretic clarity.
Now, before we look at the precise trace formula, we have to lock in 3 distinct parameters, because they're the absolute keys to this translation. First, the syzygy index P corresponds to our dominant cow-weight vector, which is essentially the particle number. Second, Q tracks our derived ghost shift. Think of that as the physical spin. And finally, the Clifford index. This is the very thing Green's conjecture is trying to map, and it becomes the total code distance, or the analytic conductor of the automorphic representation.
Focusing in on the dictionary formula for eigensheaf weights, here is where it gets wild. If the classical Koszul group vanishes at Q equals 2, which remember is the critical value for Green's conjecture, the equation just collapses. This collapse forces the pth fundamental Hecke operator to have 0 anomalous geometric weight at that exact degree, meaning the field equations remain entirely unperturbed.
All right, part 3, resolution flattening via Satake.
You can think of the Satake isomorphism conceptually as a massive global encoder. When a special curve distorts the resolution path, this isomorphism steps right in to reparameterize those irregularities into continuous Langlands parameters. It's a mathematical bridge that totally rescues us. It pulls us out of the stubborn, local p-adic operator algebra and drops us directly into the smooth, highly manageable world of symmetric polynomials over the complex Langlands dual group.
So the Satake isomorphism acts as this global encoder, forcing those local p-adic operators to behave like a rigid error-correcting template. And the best part? It's completely indifferent to how highly specialized the input carve is. You feed it local geometric irregularities and Clifford index distortions on one end, and it just smoothly outputs continuous Langlands parameters on the other. It flattens the resolution absolutely perfectly.
That brings us to part 4, L functions and prim fibers.
With our resolution successfully flattened, we route the whole problem through the Hitchin fibration to establish a definitive spectral gap. By hitting the prim fibers with the Fourier-Mukai transform, a mathematical decoupling occurs. This decoupling forces the transformed syzygy sheaf entirely out of the negative energy sectors of the J operator. The transform literally vaults the math right over that spectral gap threshold, which forces the Koszul cohomology group to 0 without ever needing the curve to be generic.
The real crux of it all is this functional equation. L of S pi r equals epsilon of S pi r times L of 1 minus S pi dual r. This global L function is acting as a partition function that computes the fidelity of our underlying error-correcting code. It proves that any non-vanishing Koszul group would imply an impossible, localized violation of the global product formula in the Adelic system.
So the Clifford index is structurally forced to match the analytic distribution of the zeros.
Moving on to Part 5, Stabilizing Ramification Defects. But we have to ask, what mathematically happens when we run into exceptional curves that cause severe geometric singularities? When a curve has exceptional gonality, which just means it admits a specialized, low-degree branched covering violating generic bounds, the high ramification index forces the spectral curve of the Hitchin fibration to develop really severe singularities. The singular prime fiber literally becomes a tangled mess, and the local Galar representation restricts to an inertia group that doesn't act trivially. This causes a massive jump in the Artin conductor.
This is where we break down the Adelic Langlands root number formula. Here, the local epsilon factor acts as our topological stabilizer. The W term is the local root number, functioning as a complex scattering matrix phase shift. Meanwhile, the scaling power, p to the negative f of sigma p, acts as a localized mass insertion to precisely counter the singular geometry we just talked about. The formula dynamically compensates for all that crazy ramification.
Through the Lemon transform, the wildly fluctuating phase vectors induced by that exceptional covering are precisely rotated. This phase calibration completely maps the irregular singular support back to a regular tame boundary condition in dual Fourier space. The result? Coherent interference. The geometric anomaly is totally canceled out.
Now, even though the local L function collapses and flattens into a polynomial due to this ramification, mostly because the inertia invariant subspace shrinks, the global epsilon factor swoops in to save the day. It calculates the exact quantum phase corrections needed to patch these localized fractures. So, arithmetically speaking, space-time remains perfectly smooth.
And finally, Part 6, the grand synthesis cycle.
By walking through these three vital steps, first, defining our moduli space on the Beilinson Drinfeld Grassmannian, second, using the modification map to pull back our eigensheaf, and third, projecting it forward, we establish the universal Hecke correspondence over the derived category of perverse coherent sheaves. This is exactly how we link the spatial positions of Hecke modifications directly to the geometric loci that organize our syzygy modules.
Notice the perfect fusion happening here. The exact same geometric point on the curve xi dictates the localized evaluation points of the canonical line bundle for classical Koszul geometry. But simultaneously, that exact same coordinate tracks the jumping modifications where loop configurations flip topological invariants for Adelic Hecke theory. It is an absolutely flawless match.
And it all culminates in our explicit psychoidentity. In this derived equivalence equation, the derived global sections functor over the BD Grassmannian perfectly equates to the classical vector spaces of the Koszul syzygies. It physically shows that moving a point along the curve smoothly deforms both the local loop group structure and the algebraic relations in exact, mathematically rigid unison.
This whole mathematical journey leaves us with a pretty profound realization. Through the Adelic Langlands program, computing the scattering of a Hecke field excitation is mathematically identical to calculating the geometric syzygy modules of a curve. It really forces us to ask, are the deep, complex algebraic relations of the universe simply the shadow of geometric Langlands field excitations playing out across the adeles? That is definitely something to chew on. Until next time.